All right, so that's this derivative here. Is that cool? 6 times 1 over x. What's this guy's derivative?
3, 1 minus x.
Times the derivative of 1 minus x, which is?
Minus 1.
I like it. So y prime is 6 over x plus 3 over 1 minus x.
Should we continue on this point?
And if you really wanted to, you can get like denominators. But if all I'm asking you to do is take a derivative, you can stop there. There's no point in going further, right? If I was asking you, where is this thing horizontal, then you want to get like denominators. So you can set the top equal to 0, right? But I'm not asking you to do anything further, so dear God, stop there. Don't waste time. Dear God. So if I just ask you for a derivative, simple simplification. Don't write this. The negative is positive. Write that. Come on. 2 times 3 is 6. Those kind of things you should do. But you don't have to factor in stuff if I don't ask you to do a next step. Does that make sense? If I'm not asking you to do something with the derivative, just find it, do any simple simplification, and stop. There's no need to factor, because you would only factor if I wanted you to set it equal to 0, right? But you can if you want to. Practice is good. If you wanted to test, you're wasting time. All right, how do we feel? So now we know ln's basic rule, and it fits into anything else. It's just like there's a chain rule and all that kind of stuff. It's just ln has a lot of ways to simplify it, possibly. What about this here? Real quick, 2 little tiny quick examples. What can I do with that before I take a derivative? Move the 2 down. And then its derivative would be 2 over x. I like it. So when you square the inside, if you double the inside, the slope doesn't change. If you square the inside, the slope does become double what it used to be. Do you guys see what I'm saying? Slope normally would be 1 over x. If I square the inside, it becomes 2 over x. Interesting. Cube the inside. Right? Is that good? But what about this? Obviously something different here. Can I take a 2 down? No, because it's not a power of the argument, right? People get really confused and they make problems become a lot easier, but also very wrong. You can't take that 2 down because the log only has a property for when the power is on the argument. This is natural log of x times x. And then I can use the sum, right, this formula here, and that's why the 2 comes down. That's why it does, because it's based off of the multiplication rule. This is ln x times ln x. Oh shit. So how do I take this guy's derivative? Beautiful, right? The first thing is just anything squared's derivative would be what? Good. Now that makes it feel that's the derivative making that 2 come down, right? Alright. So the first power now, right? Times the derivative of the inside. That's the first power. Let me not even put it there. The derivative of the inside is
1 over x.
So you get y prime is 2 ln x over x. Yeah. Appropriately freaky. If I square an ln, that gets freaky. This is not freaky. I can simplify that really easily. Okay, maybe. So let's talk about inverse trig. That's right. It's Monday, so screw you, clock. Let's see. So, how would you investigate this, for example? First off, let me really see what you guys remember. What is the domain of this function?
You have to set.
So real quick, let's remember where this came from. What sign looked like? I like it. All right, cool. I just want to see you guys do that. So that's basically sine, right? In order for a function to have an inverse, it has to pass horizontal. Does that have any chance the way it is? Has no chance. So what do we do? Do you guys remember this? In order to say that I have an inverse function, I have to restrict this guy's domain.
Negative pi over 2.
Good. So it goes from negative pi over 2 to pi over 2. Cosine, for similar reasons, cosine would look like this. Woo. Cosine, I can just restrict it from 0 to pi. You guys see that? Does that sound familiar? And this is why when you did the inverse trig, your answer was a reference angle. And you had to remember to get it in the right quadrant. Does that sort of come back to you? Those dark days? Well, for some of us it was dark days. So how does this relate to that, though? That is the what of this. This is the what of this. That's the domain of the sine function that I'm restricting it. So that is the range. The range, of course, would be negative pi over 2 to pi over 2. The domain, of course, would be related to this guy's range, which is
negative 1
to 1. I like it. If you know the original function's domain and range, the inverse function just switches those because the inverse function switches all the x's and y's. So of course it's going to switch the range and the domain. How are we feeling at the moment? Okay, good. This is a nice summary. Now, how do I do this then with that stuff in the background? Somehow that's going to affect us in some places, but how do I just take this guy's derivative? If I don't know it, how do I do it?
Sine y equals.
Good. Take the sine of both sides. So sine y equals x. Man, that's crazy.
So derivative.
And then you can do the derivative, because now I know implicit differentiation, we just got a lot stronger. It's like we went from 4 to 8 on fallout. It's crazy. I just want to see what that there.
dy dx.
Yeah, so how do I take this guy's derivative?
Cosine y.
So I want to do d by dx sine y and d by dx. Let me just write all the forms for us for once. So what's the derivative of sine with respect to x? Sine y with respect to x?
Cosine.
Cosine y
dy dx.
dy dx equals
1.
1. That's crazy. So then dy dx equals
1 over cosine y.
which is not good enough, right? You guys see why that's not good enough for a general definition? If I have a function of x to begin with, I want its derivative written as a function of x also. Right? If possible. It's not always possible, but here it totally is.
Can we use trigonometric properties? Like
You better.
cosine.
I'm sorry. Yes.
Cosine squared y plus sine.
Yes, you could. Yeah, totally. If I know sine y is x, and I do, because that's where we started, isn't it? Sine y is x. How do you get cosine y?
Square root 1 minus.
Take derivative of those.
Cosine.
Yeah, because cosine y equals square root of 1 minus sine squared y. Right? Plus or minus and all that kind of stuff. Uh-oh.
So I did it in my homework, but you also showed us triangle method.
Exactly. Or you could start from the very first spot. Right? So what's this setup for me?
So y over y.
So x
Oh,
is 1 is a hypotenuse. Hypotenuse.
1 is the hypotenuse, and x is the y side,
So it's going to be square root 1 minus x squared.
which is what we would get here anyway, right?
Yeah.
We doing all right so far? I love you guys. Like, you just go for it. So then what's cosine y? So this angle, what is this angle really? What should I put there? This angle is y. So what's cosine y?
Cosine.
Square root of 1 over x squared over 1. Or so.
Yeah, square root of 1 minus x squared over 1. So square root of 1 minus x squared. And then cosine would be the same thing, except what would happen right here if there was a cosine here instead? The derivative would have been negative sine. So cosine, the derivative of inverse cosine is negative 1 over square root of 1 minus x squared. And I think they collect, do they collect? They collect these at the bottom of page 214. I don't know if you remember, I said this last time, I'm not going to make you memorize these, because I haven't got these memorized, to be honest. I just never saw a point to it, so I didn't do it. And similarly, the same exact way, you could figure out, so here, you guys take a second, or several, and figure out what the derivative of this is.
What if I already know that? Can I just tell you?
No. Figure it out. I don't know what to say. Math, so it's good to know things. It's obviously good, because then you can use it. But math is, what's more important in math is not the number of facts you know, it's the number of procedures you know. So this is just getting the procedure down. So any inverse function I come across, I can apply the same procedure. Cool. Sorry, Kevin.
Yeah, that's
I like that you know it.
That's what somebody was like, you want me to say or you want me
No, do it. Prove it.
Yeah.
Prove it.
One over 1 plus x squared.
Let's stop on that. Just a second, John. So real quick, before we get into it, you can set up this. Which side is x?
So,
X is X. Or X is the opposite. It's Y.
X is the y side. And 1 is the
Is the
x side. I like it because it's tangent, right?
Yeah.
So if I need it, I know that this is going to be what?
X squared plus 1.
I like it. Cool. So when I do this, I get tangent y equals x. That's the first step, is to take the tangent of both sides. So the inverse tangent goes away. Derivative of tangent is secant squared
Y, dy dx
dy dx.
equals 1.
So dy dx equals 1 over secant squared. And what's secant?
Secant is 1 plus tangent. Secant squared
secant is
y.
hypotenuse over
Secant
X.
squared y.
Damn it.
So we square root of x squared plus 1 over 1. So secant squared will just be x squared plus 1. So that's the derivative of inverse tangent. It's 1 over x squared plus 1. So what do you think the derivative of inverse tangent might be? That's insane. But that's right. So I'm sorry. That's correct. So again, it's on the bottom of page 214 if you want to reference those. Okay, what was the last thing I wanted to do? Oh, yeah, that's right. That's right. I always forget to do this until we get to intervals, so I might as well do it right now. Going back a step to my ln. My ln. What does 1 over x look like? I like it like that. That's what I want to see. So it's like this, like that. Is that cool? That's 1 over x. What does ln look like?
ln is all positive, right? Or is it only?
No and no. So where's it crossed here?
Yeah.
At 1?
Alright, so it's only this.
And it goes from
Fix
negative
that and ask
to
yourself down.
Yeah, because it has an asymptote there. I like it. So, now what did we figure out before? We figured out that d by dx ln x equals 1 over x, right? And just to see if this makes sense, well, the slope here is really big, positive. The slope is very big positive. That's why it's up here, right? For the derivative, this is true. We proved this. So the graph better follow what it's supposed to do. Sure enough, that's really big positive values because the slope of this would be really big positive, and the slope becomes closer and closer to
0.
but never quite gets to.
0.
And that's why that makes sense. But then what doesn't make sense up here then?
the other side.
There's, yeah. Sorry. So, the reality is, and this becomes really important when we get to anti-differentiation, the opposite of derivatives, right? Which is easier than you think. What do you think that, if this is y prime, what must y have been?
Y.
If this is y prime, what must y have been? It must have been x cubed. That 3 would go back up, right? You guys see that? You just integrated it. Hey, good job. So that's the second half, and the second, like the last third of this class is going to be talking about what we call intervals, which is anti-differentiation. Is the long-ass way to say it. So it's going to become very important then. But to complete this picture now, I do this. D by dx of this. And once I do that, what am I allowed to do now? That I wasn't allowed to do at first. I can put, what kind of x's in there can I put now? Negative x's. So I get the same thing, mirror image. And that's here. Slope here is almost
Almost zero.
0. See? And then it's getting more and more negative. More and more negative. You guys follow? So that makes the picture complete. So this is the most general way to write the rule. The derivative of ln of absolute value of x is 1 over x. Then you get the complete picture. You guys start to see what I'm saying? Does that affect you at all when I do the derivative of ln of x? No. You don't give a shit. You just know inherently that what's x got to do? What's the domain of this? What's the domain of this?
It's from 0 to infinity.
So when you do its derivative, it's also got that domain. Right? Now in general this has got more, but since I wasn't allowed to use negative x's to begin with, I can't suddenly use them now. You start to see what I'm saying? A little bit? Like this much? Shit. Alright. I think they talk about it in the book somewhere. Page 220, they do something really weird that's related to this. If you want to look at that, that was really a glowing recommendation. By the way, page 229, we're going to get into 3.7 next, not today. Page 229 actually starts at the bottom, page 228 has a problem that was in homework earlier. So I'm always curious if somebody found and just copied. But it's there, they actually work it all the way out. It looks very familiar. I don't remember which problem it is. Example 5 in section 3.7 is an earlier homework problem worked out for you. Don't you love it when they tell you after the fact? I love it. I like it. I think that is enough for today. What do you guys think?
Yes.
So on Wednesday, quiz 3.5 and 3.6. Implicit differentiation, arc, trig, which you don't have to memorize. So if I ask you a question, I'll give it to you. But ln, you definitely have to know. That was an easy one. That's plenty. I'll let you out. Really.
Take the ln on both sides.
No, we haven't done that yet. Is that in there? I always forget about that. Oh, that's cool shit. It won't be on the quiz. Yeah. Glad that was in there. That's right. Thank you.
Did you want to